Mathematics is not about numbers, equations, computations, or algorithms. It is about understanding. These golden words from William Paul Thurston resonate with me as a polymathic educator and narrator. Mathematics is precise, and in part, it is due to how mathematics best translates the accurate understanding of something. Graphs are one means and also one end to get to see our understanding of functions. Let us graph the 6 trigonometric functions. Graphing the 6 trigonometric functions will require comprehensive insights into the behavior of the functions, as well as a fair grasp of graphs. We are already through the conceptual and visual appreciation of graphing and asymptotes. Thus, we may just dive in straight away. The unit circle is a powerful way to represent wave motion, which is inherently periodic. At any moment, it combines two types of movement, a horizontal or forward motion, and a vertical motion that defines the wave's rise and fall. In the animation, the blue line shows the horizontal progression over one complete cycle, or period. The red line illustrates the vertical oscillation, which shapes the wave's peaks and troughs. Together, these motions show how circular movement translates into the repeating patterns of a wave, with the length of the blue line representing one full period. This circular motion transforms into the familiar sine wave pattern used in trigonometry. As you watch the animation, notice how circular motion unfolds in 2 dimensions and how it forms a right triangle in motion. This is what makes trigonometry so useful here. Each point on the circle's circumference gives us 2 values, the x and y coordinates. These aren't just random numbers, and they represent the lengths of sides of the right-angled triangle. In a unit circle, the x-coordinate is the cosine of the angle, and the y-coordinate is the sine of the acute angle of the triangle subtended at the center. That's why circular motion naturally leads us to trigonometric functions and gets us ready to start graphing sine and cosine waves. We are now ready for graphing the functions. The sine and cosine graphs are the first important trigonometric graphs. To clearly compare them, both are shown together in the same graph. In this animation, the red curve represents vertical motion and corresponds to the sine function, while the blue curve represents horizontal motion and corresponds to the cosine function. By definition, cosine values are measured along the x-axis and sine values along the y-axis. This distinction in how sine and cosine are derived and creates their most recognizable feature. They are out of phase, meaning one function begins where the other reaches its peak. This phase difference is key to understanding their behavior in wave motion and periodic phenomena. Sine and cosine functions show similar wave-like behavior but are out of phase, meaning they reach their peak values at different times or angles during the circular motion. Specifically, cosine leads sine. At angle 0, the cosine value is 1 while sine is 0. As rotation continues, this phase difference persists. When one function is at a peak, the other is at 0. This phase shift becomes clear when visualized on the unit circle. Since cosine starts at its maximum 1 and sine starts at 0, the cosine graph appears to lead. A part of this is due to mathematical convention. Movement to the left, negative x direction, is seen as decreasing. That's why the cosine curve drops from 1 to negative 1 as the angle moves from 0 to pi radians. Also, angle direction matters. As per convention, anti-clockwise rotation is considered positive, while clockwise is negative. So 270 degrees is a positive turn from 0, while minus 90 degrees is a clockwise turn reaching the same point on the circle. While we're at it, let's visualize what sine theta plus 2 or sine theta minus 2 might look like. The graphs below show sine theta along with its shifted versions. Adding or subtracting a value to sine theta shifts the entire curve up or down without changing its shape. What happens when the angle in a sine function is multiplied or divided? This affects the speed of the wave's cycle, thus its wavelength and frequency. One circular motion could be made faster or slower. If the angle is multiplied by a number greater than 1, the sine wave completes its cycle more quickly, meaning more cycles occur in the same interval, and the wave appears compressed horizontally. This reflects faster oscillation or higher frequency. On the other hand, if the angle is divided by a number, the wave stretches out horizontally, completing fewer cycles in the same interval, indicating a slower oscillation or lower frequency. This is also called horizontal scaling of sine wave. Multiplying by a number outside the sine function, like 2 or 5, scales the sine waves. It changes the height of the wave but not the frequency or period. Sine theta has a maximum value of 1 and minus 1, thus 2 sine theta will have a maximum value of 2 and minus 2. This is also called vertical scaling of sine waves. Let us understand phase shift in sine waves. A phase shift means the curve moves horizontally either to the left or to the right, but note, the values of the function don't change and the shape of the sine wave stays the same. What's actually changing is the starting point of the wave. So when we subtract an angle, say pi by 4 or pi from theta, we're shifting the entire sine wave to the right by that amount. This creates a delay in the wave's start. For example, sine theta minus pi by 4 starts pi by 4 units later than the regular sine wave. Sine theta minus pi starts a full pi unit later. This means that the usual sine values occur at different angles or times. They are shifted horizontally on the graph. In the graph, we can see how these curves follow the same pattern but begin further along the x-axis, showing a clear horizontal shift. This is how phase shifts appear in both equations and graphs. Let us now look at what happens when we add an angle inside the sine function. Quite expectedly, adding an angle means the sine curve starts earlier than usual, so it appears shifted to the left on the graph. This is a left phase shift, or left horizontal shift of the curve along the x-axis. Take the example of sine theta plus pi by 2. When theta is 0, this becomes sine pi by 2, which equals 1. That means the sine curve reaches 1 even before the standard sine curve would have started rising. It's as if the whole wave has moved pi by 2 units to the left. It doesn't change the values of the sine function, only when those values occur. Compare that to a vertical shift, which would change the actual value of the sine at every point. So remember, fx equal to sine x minus pi by 4 shifts right by pi by 4. Fx equal to sine x plus pi by 4 shifts left by pi by 4. We have already seen how the sine and cosine graphs behave. Now let's take a look at the tangent function, which is simply the ratio of sine to cosine. Because tangent is a rational function, that is, one function divided by another, we can apply rational graphing methods to understand its shape and behavior. Understanding sine and cosine makes it much easier to grasp other trigonometric functions like cosecant, secant, and cotangent, because they are just reciprocals of these base functions. Here's something important about tan theta colon. Whenever the denominator, that's the cosine becomes 0, the function becomes undefined. This leads to vertical asymptotes in the graph, and they appear at every odd multiple of pi by 2, such as pi by 2, 3 pi by 2, and so on. Also, because both sine and cosine are of the same degree, there are no horizontal asymptotes in the tangent graph. So, by understanding how sine and cosine behave, we can easily predict and sketch the graph of tangent too. Let's now look at the graph of cotangent, or cot of theta. In this function, sine is in the denominator, so wherever sine becomes 0, cotangent becomes undefined. Sine is 0 at angles like 0, pi, 2 pi, and so on, that is at integer multiples of pi. So you'll see vertical asymptotes in the graph of cotangent at these angles. In short, wherever sine theta is 0, cotangent theta shoots off to infinity or minus infinity, just like tangent did when cosine was 0. Let's look at the cosec function. It is reciprocal of sine theta. Since sine is in the denominator, wherever sine theta is 0, the function becomes undefined. That means there are vertical asymptotes at those points, and we know that sine is 0 when theta is 0, pi, 2 pi, and so on. So the graph of cosec theta will have vertical asymptotes at integer multiples of pi. Like other reciprocal functions, the curve of cosec stays far from the x-axis and follows the peaks and valleys of the sine curve, but never touches it. Now let's look at the secant function, written as sec theta is reciprocal of cos theta. This is also a reciprocal function, this time with cosine in the denominator. So wherever cos theta is 0, the function becomes undefined. We know cosine is 0 at theta is half pi, 3 by 2 pi, and 5 by 2 pi, and so on. In other words, at odd multiples of half pi. At these points, sec theta is plus or minus infinity. As a closing note, let's observe how the values of sine and cosine change across a quadrant and how that change is not uniform. Take the sine function, for example. At 45 degrees, halfway through the first quadrant, the value of sine is already about 0.7. That's 70% of its maximum, which is 1, the length of the radius. So sine rises quickly in the first half of the quadrant. The second half contributes only the remaining 30%. In fact, in the last 10 degrees, from 80 degrees to 90 degrees, sine increases by only about 2%. Now compare this with cosine. At 45 degrees, cosine is also 0.7, which means it has only dropped 30% from its maximum value of 1, the length of the radius. So, cosine decreases slowly in the first half of the quadrant and drops more steeply later. This shows us that even in uniform circular motion, the rate at which x and y values change isn't even. Sine increases rapidly, while cosine decreases gradually in the same interval. We are now ready to explore trigonometric equations, relationships of quantities that harness trigonometric functions. Thank you. With us, you will master all the mathematics you need. Be good to you, not just others.